Thanks everyone for coming, and today I want to discuss about the algorithm we developed at Surrey, and also I want to discuss about how to improve when there is limited monitoring data, or how many training data we need for a reliable machine learning algorithm. So firstly, I will introduce the background of this topic, and then I will show the methodology, the algorithm we developed. And then I will show two laboratory case studies. One is in my paper. The second one is actually our recent result. So it's not in the paper, but I will show here. Because it's an ongoing project and ongoing research, I would like to provide some discussions instead of conclusions. So firstly, I want to draw your attention because we all know civil infrastructure systems inevitably degrade, but they are very important to support people's life as society. But maintenance cost for the infrastructure system costs more than 20% of the whole life cost for infrastructure system. So it's very important. That's why around 30 years ago, structural health monitoring was proposed and introduced to civil engineering domain to aiming to detect structural damage before it's become a bigger problem. But recent development of emerging technologies has enabled structural health monitoring enter a new stage. Okay, so it involves some IoT, Internet of Things development, and artificial intelligence research, and digital twin. So all these emerging technologies contribute to the not so traditional, but it's existing research direction, structural health monitoring. And because of these emerging technologies, we can see now structural health monitoring has a data-centric fashion. So, for example, structural modeling, we use finite element modeling. We can get the structural behavior data. And from the sensor and data acquisition system, we can get the measurement data. And from this simulation data and measurement data, we can do the structural condition identification and data analytics. So the data will be used. And also we can do the real-time model updating to update our numerical data, which become a digital twin. And then the data will be used for maintenance and life prediction for the civil infrastructure. Since the significance of data is very important, data-driven method has actually shown very good results recently. And especially deep learning algorithm has stand out as it enabled the modeling of complexity and nonlinearity by using multiple layers. Okay, so that's why I'm choosing deep learning algorithm for structural condition identification. So actually, this is using deep learning algorithm. We are using a so-called data-driven structural health monitoring method. Normally, the structural health monitoring can be divided by physics-based, which is normally we need a physics-based model, finite element model, for example. But the other kind of method is data-driven. So we don't use a physics-based model. We just use the data, monitoring data. So this is the data-driven method. But the problem for the traditional data-driven structural health monitoring method is its lack of training data, actually. If we imagine there is a bridge and it is in operation and we collect data every day, that's massive data, I agree. However, if you imagine there are only one condition, if there is no damage happened during one day, for example, this one day you have only one healthy structure condition. And if we consider there are damages, the damage can happen in any location of the structure, or it can have different levels of severities. So there are the possibility of damage or the change of condition of the structure is actually infinite. The possibility is infinite. So that's why we think the data-driven method actually almost always suffer from the lack of training data. So we don't have enough data to train reliable machine learning algorithm. But we could generate training data from laboratory tests or from the simulations. For example, if we mimic the real structure in the laboratory and we do some tests and we change the condition from the laboratory specimen, we can generate some training data. Or we do some numerical simulation, we can generate different scenarios, we can generate training data as well. In this project, we use the test method. We create a laboratory specimen, and then we change the condition of the laboratory specimen, and then to generate the training data. But if we know this, but we still don't know how many training data are needed, because for laboratory tests, for example, if we use impact hammer testing, normally we need to do repeated hammer testing for the monitoring purpose or model identification purpose. But how many repeated tests are needed, we don't know. Especially for data-driven algorithm, we don't know. That's what we want to answer in this paper. So in our, we have three choices for the excitation. One is impact hammer, the second one is a shaker, the third one is operational vibration. But in the laboratory environment, we use impact hammer test because it's easy to control, and it's we don't need very high power to do the test. So in this project, we use impact hammer test. And also for the algorithm, we use time domain acceleration data directly. We didn't transform it into the frequency domain because it will be more efficient, and this time domain acceleration data essentially contain all the vibration information, including the transient information. And in this approach, we use the acceleration data itself, labeled data itself as the training data, and then input into a 1D convolutional neural network model, and then we get the classification result. And based on some criteria, we've optimize this 1D CNN model so that there are a few, not a few, actually 500 iterations to optimize a 1D CNN algorithm. And then we use the rest data to test whether our 1D the learned model 1D CNN is effective in condition identification. Our data are normalized according to the impact excitation. So it means we normalize the input itself. The input will be normalized to 1. So every time the hitting force may be different, but we normalize to 1. And then the acceleration itself, we normalize based on the ratio between the excitation. And 1D CNN architecture, actually, we choose a very iconic neural network, AlexNet, which has increased the accuracy around 20% from 70-something to 90-something in 2012 ImageNet competition in the image analysis domain. But we adapt that because the normal deep learning algorithms are all for images. So they are essentially 2D. We adapted to 1D. And then we also choose another optimization algorithm named Adam for the optimization of the neural network 1D CNN, which is proposed in 2015, I think, but it has received lots of attention, and the optimization performance is very good, so we choose that one. Then basically, our architecture is like this. In my paper, there are very detailed architecture. Actually, if you use Python, if you see the architecture shown in my paper, you can do the same program as mine. Now we come to the laboratory test. First one is still Warren Truss bridge scale model, and we quickly go through that. So we put 3 accelerometers at here, and then the impact hammer is here. And we created 7 scenarios. One is intact structure. The rest 6 are damaged scenarios. And for each scenario, we did 5 repeated tests. And from the model identification result, we find out it's very hard for us to identify all the modes. For example, for damage scenario 3, we cannot find the first mode. We cannot find the third mode. So it's very hard for us to do that. Even for damping ratio, it's a similar result. And even we have some result here, the changes is not evident. But what we do is, by using our developed algorithm, use the training data. I have used one data set, 2 data sets, 3 data sets, and 4 data set to train 4 CNN models, and then get this trend. And we see after 500 iteration, the training accuracy becomes stabilized. So we choose to stop here. And now we have 4 1D CNN models trained by using 1 data set until 4 data sets, and we use the rest of testing data to test the result. We found if we just use 1, only 50% accuracy, but use 4 is 100%. The second case study is in the laboratory is steel frame structure, and we use 6 accelerometers, but this time we use 10 repeated tests performed per scenarios. And there are 10 scenarios actually, and we try to simulate the structural damage as small as 1 bolt loosened. The existing study, based on our knowledge, all are focusing on all bolts loosened at one connection, but we focus on 1 bolt loosened. And from the model identification result, we found out only tenths when all bolts is loosened, there are some changes from the model frequency. From the damping ratio, we can see only the second mode damping ratio has some changes. But it's very hard to identify because model damping ratio is not easy to use as indicator. But using the deep learning algorithm, we found out if we use just 1, we can reach actually 80% accuracy. Use 4 and 5, we can reach 100%. So there are some consensus after these 2 laboratory case study. 100% accuracy can be achieved if we use 4 repeated tests. Imagine I test 10 times, but with only 4 repeated tests as training, we can achieve result. Traditional model-based method essentially fails because there is no changes. And with data, training data per scenario, we have worse accuracy results, but still you have some result at 80%, so it's not very bad. So the future research for this area, I believe we can change the monitoring data from impact hammer to operational vibration, and also use numerical simulation data as the training data. And then, is there any alternative ways to generate more training data? I provide one alternative in my paper. Yeah. I want to acknowledge my researchers in my team, and yeah, thank you. Sorry for that.